this is the outline for chapter 30. So you can see there's quite a lot of items here. So first we'll talk about the Faraday's Law, and actually we'll also talk about the Lenz's Law, which is only the minor sign in the Faraday's Law, and then we also already call it Lenz's Law. And next we'll talk about induction, and then energy transfer for the inductor, something like that. And then we will rigorously talk about what is inductor and inductance, and then the induced E field. And then we'll talk about self-induction, some circuit theory, but yeah, maybe you might not be understand it easy because I've not talked about the differential, how to solve differential equation yet. After finish this chapter, I will talk about how to solve the constant coefficient ODE. So which is some supplementary mathematics for this course later on. But yeah, just try to know a bit, and then maybe we'll know how you'll be like that later. And then we'll also talk about the energy stored in the magnetic field, similar to energy stored in the electric field when we talk about the capacitor. Okay, so we also talk about the energy density in the magnetic field, and then finally we'll talk about the mutual induction, or maybe you might have heard about the transformer. Actually, the mutual inductance is somehow like the transformer. Okay, so here we talk about the Faraday's Law. So it introduced this Faraday's Law with some experiments. So the first experiment is like we have a setup like this. So it says a conducting loop is connected to a sensitive ammeter. So this is a conducting loop. You can see this is somehow like a circle, and then with this wire connecting to the ammeter. So this is ammeter to measure the current. Because the SI unit for the current is ampere. So this is called ammeter. And if we have a device to measure the voltage, we call it voltmeter. Voltmeter for measuring voltage. Okay, so here sensitive means it can send some very small current. Sensitive usually means it can measure some small current. Okay, so because there is no battery or other source of EMF induced, there is no current in the circuit. So in previous chapter, like chapter 26, we know if we should have a battery. If we have a resistor here, and then we should have a battery to provide some potential difference so that there will be current. But here we don't have any battery. So initially, without considering this magnetic bar, then there will be no current going through this loop. Okay, so however, if we move a bar magnet towards the loop, a current suddenly appears in the circuit. The current disappears when the magnet stops moving. So initially we don't have this one, and then we try to hold a magnet bar and then try to put it close to this loop. Then suddenly there will be some current. Going through this loop. But if we still hold the magnet, but we stop, but the magnet bar still close to this loop, we don't have any current. The current disappears when the magnet stops, but still holding there. Okay, if we then move the magnet away, a current again suddenly appears, but now in the opposite direction. So this current, this so-called induced current, related to the movement of this magnet bar, not actually the existence of the magnet bar. Initially we don't have the magnet bar, we don't have current. We put this one close to this coil, then in between there will be current. But even if we hold the magnet bar here without any movement, then we don't have current. And then we try to move it away, there will be current, but in opposite direction. So it relates to the movement, but not the existence. Okay. So here it says, if we experiment for a while, we would discover the following. So a current appears only if there is relative motion. Relative motion. I just said movement, but in a more physics way, it's called relative motion. Relative motion means you can move this close to the coil, this one without moving, or if you just hold the magnet bar there and then you try to move this whole structure close to this magnet bar, it is still relative motion. But if you move this one and this one with the whole with the same velocity, then there will be no relative motion, right? Yeah. Okay. So the important thing is the relative motion. The relative motion. So between the loop and the magnet, one must move relative to the other. So the current disappears when the relative motion between them cease. Cease means stops. Okay, so fast motion of the, and then there are 3 points. There are 3 points. So for the fast motion, for the fast motion of the magnet produce greater current. Faster, greater. And then the second one, if moving the magnet north pole toward the loop cause, say, clockwise current, then moving the north pole away will cause counterclockwise current. Yeah, clockwise. Yeah. A few pages later, you'll know why it will be clockwise and then counterclockwise. Using the Lenz's law, we'll know how to determine the direction of this induced EMF. EMF, you can, here it talks about the E. It does not talk about the EMF yet, but we'll introduce what is EMF later. It is somehow close to the electric potential, but not actually the same. So the third point is moving the south pole towards or away from the loop cause current, but in the reverse direction from the north pole. So the pole, whether it is north pole or south pole, really matters. Okay, so far we have these 3 points. These 2 points related to the direction of the current, and the first point related to the amplitude of the current. Okay, so here is another experiment. It's a second experiment. So for this one, you can see this part is actually the same with the previous one, but we do not use the magnet bar anymore. We change the magnet bar into another loop coil, but here we have a battery and a resistance, so that if this switch is closed, then it will generate a fixed current here. Okay. But of course, if it is open, then there will be no current because the current cannot go through this part. Okay, so it says for this experiment, we use the apparatus with the 2 conducting loops close to each other, but not touching. So in this case, we don't necessarily need to move this one. We just try to switch it on and off. Switch it on and off without actually the relative motion. Okay, so here, if we close the switch, which means like this, close the switch to turn on a current in the right hand loop, the meter suddenly and briefly register a current, an induced current in the left hand loop. Okay, so when you most of you are Chinese, so in Chinese, somehow you make it like the other way around. So because in Chinese, you say 开跟关, and actually the close means 开, close means 开, and then open means 关. So actually, you should be familiar with this language. So close means try to switch it on. Close means try to switch it on to make it short. And then to open it means to open it. This is open. This is open, so that there will be no current can go through. Okay. So so it says when the switch is closed, the meter suddenly and briefly register a current. Somehow like when we try to put a magnet bar close to this the left part, then there will be current. Then there will be current, which means that there will be current going like this. Okay, so yeah. Okay, so if the switch remain closed, no further current is observed. Similar to the previous case, when we try to hold the magnet bar there, then there will be no current. And here, if we just remain the switch closed, then no further current is observed. Then we try to open the switch. And other sudden and brief induced current appear in the left-hand loop, but in the opposite direction. So actually, it is similar to the previous case, but here we don't have any relative motion. We use this switching on and off motion to replace this relative motion. But we can still observe similar phenomena. Okay, we get an induced current only when the current in the right-hand loop is changing. So here, changing is the keyword. Either turning on or turning off, and not when it is constant. When it's constant, then there will be no induced current for the left loop. The induced EMF. Induced EMF is somehow like the electric potential, but not actually the same, because here when we have some induced current, it should be somehow like there should be something to push the current to move, but we don't have a discrete battery there to provide the potential difference. So in that case, it should be somehow like for this loop, there is somehow like the EMF in this direction, and also the current are also in the same direction. But you can regard it like, for example, if the whole EMF is, for example, 10 millivolt, and then this is 0 volt. So the EMF is still have the same SI unit with the potential difference. So we use a volt for it. But you can regard it as this is 10 millivolt. So here will be 5 millivolt. This is 7.5 millivolt. Somehow like that. This is 2.5 millivolt. So the EMF gradually consumed by the loop. So this EMF push the current. Yeah. So you can regard it like this. But yeah, similar to a battery, but not actually the same. It is somehow like equally distributed for the loop. A little bit hard to understand, but yeah, I think yeah. But yeah, actually for EC students, they should also study the electromagnetism in the forthcoming chapters. But yeah, for most of you are civil engineer students, so I don't think you will touch it anymore in the later semester. Okay, so yeah, so actually here it says, what is that something? So it says in this experiment, of course, when something changes, we know there is something change. For the previous one, we have some relative motion. For this one, we should switch on, switch off it, so that something should be changing to make the induced current occur. So, but what is that something? And then it says Faraday's law. So finally, we call it the Faraday's law. Okay, so here, Faraday's law of induction. So Faraday realized an EMF, electromotive force, motive force. In Chinese, it is called 电动式或者是电视能I don't really sure. Yeah. Electromotive force. This is a short form for the electromotive force. And a current. So can be induced in a loop, as in our two experiments, by changing the amount of a magnetic field passing through the loop. Okay, so it says it is related to the changing amount of the magnetic field passing through the loop. So in other words, it is so-called the magnetic flux. So when we talk about the Gauss law in chapter 23, we have the electric flux, the phi E to be something like this. I hope you still remember because we have midterm exam next week. Yeah, this is the electric flux for a closed surface or the Gaussian surface. So here we will consider the magnetic flux, but not for a closed surface, so we don't have this circle here. Okay, so here further realize that the amount of magnetic field can be visualized in terms of a magnetic field lines passing through the loop. And then the magnetic flux through an area of magnetic field is defined as this expression. So the only difference between this one and this one is that we change E to B. So we consider the flux for the B field, and then it is only for a open surface. For example, for this one, we consider this circle, which is not a closed surface. So we only integrate this B dot dA over this surface only. So we don't have these circles here, where the integral is taken over the area. And of course, we can feel free to define the direction of the dA similar to Gauss, not so similar to Gaussian surface. Because for Gaussian surface, we define a closed surface, and then the direction should always pointing outward. Will be the positive direction. But here it is open. You can either define it to be pointing this way or the other way. But finally, we should consider the right-hand rule. For example, if the current is not, for example, for this one, if the current is going like this, usually we will try to use the right-hand rule to determine the direction. So like this. So you use a forefinger following the direction of the current, and then your thumb will point to that side. Yeah, like this. So then I will try to use that side to be the positive, or the direction of the dA. Yeah, using the right-hand rule. Usually I try to do that things because you introduce too many minus signs, then you make mistakes. So yeah, and then here the SI unit for the magnetic flux is called Weber. Of course, a name, then yeah, and in short form it is written as WB or T dot M square. Both are okay. T dot M square or Weber. Or yeah. And then if B is perpendicular to the area, then yeah, so this integration, if B and A are parallel, which means that B is perpendicular to the area, and then B dot dA is nothing but B times dA, because the cosine 0 degree is 1. So, and then if B is also uniform, then this integration, or you can just put it out, and then B times integration of dA, which is nothing but the area. So we only have a B times A. So in high school, you probably should have learned this expression rather than this one, because at that time, yeah, you shouldn't have learned the surface integral in high school, but probably the physics teacher should have taught this one. Okay. So this is the magnetic flux, and then it is the Faraday's law of induction. So this is the highlight, the magnitude of the EMF, the electromotive force E induced in the conducting loop is equal to the rate at which the magnetic flux phi b through that loop changes with time. Okay, so quite long. So simply, when we just look at this equation, which is actually what it says, and I cannot find the font for this one. So here it use you write it like this, but actually in the slides I only use this epsilon to stand for that. So yeah, okay. So actually this is the equation for the Faraday's law. So we write it as E. E is the induced EMF, and then with a equals to the minus d phi b dt. So the derivative of the magnetic flux with respect to time, and then take the minus sign, is the induced EMF. Okay, so yeah, looking quite elegant. And then for the coil, of n turns, then we multiply an additional n there. So if it is one loop, then we can just use this one. If it is a 10 loop, then this one multiplied by 10. Because you can simply imagine the magnetic flux is 10 times larger, because yeah, if you have a one turn, if you have one turn and then the magnetic flux is changing, then d phi b dt is 1 times, and if you have multiple loop, then the flux is multiplied by n if you have n turn there. So nothing special. And then what we should know is that this minus sign in these two equations is referred to the Lenz's law. So yeah, for Faraday's law, it's the whole formulas. But for the Lenz's law, it only refers to the negative sign. So you can see it's not so easy to determine the direction of the EMF. Not so trivial. Yeah, and we'll have a 1 or 2 page to talk about how to determine the direction of the EMF. Although in this equation it's only a negative sign, but we should also consider the polarity of this time derivative of the magnetic flux. Okay, so yeah, before we move on, we just have a simple sample problem. So here it says the long solenoid S has 220 turns per centimeter and carries a current I. Its diameter D is this value, and its center replace a 130 turn closely packed coil C. So this one only has a 130 turns, but this one we have 220 turns per centimeter. Yeah, and yeah, so the diameter for this one is 3.2 centimeter, and then this one is smaller. The diameter is only 2.1 centimeter. So the current in the solenoid is reduced to zero at a steady rate in 25 millisecond. 25 millisecond. Yeah, because as it said, initially it is 1.5A. It reduced to zero steadily in 25 millisecond, which means that it should be something like at t equals 0, it is 1.5A, and then at 225 millisecond it reduced to 0, so it is a straight line. Okay, so the current in the solenoid is reduced to 0 at a steady state rate, and then what is the magnitude of the EMF that is induced in coil C while the current in the solenoid is changing? Okay, so we just, yeah, so first we try to calculate the magnetic flux phi B across this small coil C, because when we talk about the EMF for this one, we talk about the magnetic flux for this one rather than the larger one, because it is the source. This is how it interact to this magnetic flux changing. So here phi B is B times A. We assume the magnetic field generated by this solenoid is uniform. We have already mentioned it in chapter 29. Okay, so here B is mu 0 IN, if you still remember. The magnetic flux generated by the larger coil is mu 0 IN, and then times A. Okay, so mu 0 is 4 pi times 10 to minus 7, and then I is this 1.5A, and then times N is this 220 turns per centimeter, but we should change it to turns per meter. So it is like 220 times 100, so it becomes 22,000. And then this is mu 0 IN, and then the A should be pi, and then the diameter is 2.1 centimeter, so the radius should be 0.021 over 2. This is the radius, and then quantity square, like this. So this is the cross-section area of this coil C. Okay, so this number is nothing but 1.44 times 10 to minus 5 Weber. So this is the magnetic flux. And then the d phi b dt should be negative 1.44 times 10 to negative 5 all over 25 times 10 to minus third power. So this minus sign is because it starts from 1.5 and then it reduced to 0. So we have a negative slope here. So we have a negative sign here, and then at the beginning, the d phi b at this point is minus 1.44 times 10, and then it reduced steadily or in a constant rate. So we divide it by 25 milliseconds. So this number is negative 5.76 times 10 to minus 4 power Weber per second. Yeah, the SIU is like we divide this one by this one. So this one is Weber, this one is second. So we have Weber per second for this rate of change of the magnetic field of the magnetic flux. Okay, so we can just plug this one into the Faraday's law. So we have E equals negative N d phi b dt, d phi b dt. So this is negative. This is capital N, this is small n. So this is the number of turn per unit length. So this is the total number of turn. So this total number of turn is 130. So negative 130 times negative 5.676 times 10 to minus 4 power. So this number is 75 millivolt. Not a big value, 75 millivolt, which means 0.075 volt. So it does not ask you to determine the direction yet, so yeah, we will talk about it here for the Lenz law. And yeah, before we move on, let's have a 10 minutes break first.